Click for IB Biology, oxygen dissociation curves, the relationship between oxygen and hemoglobin transport. There's a PDF in the description which you can download and annotate with your own notes from this presentation, and then you can follow that up with the quick quiz which is in there to test your understanding of the content of this presentation. As we move forward with the discussion of oxygen transport, we introduced the idea that rather than discussing high and low concentrations of oxygen, we will be moving towards discussing the actual pressure of the gases. And although we can use these ideas interchangeably, but pressure is the way it's described and quantified. Noting that the pressure of air, standard pressure of air, is measured at 101 kilopascals. So that's a new unit, the pascal. Now, oxygen, as we know, makes up 21% of air, and therefore it makes up 21% of this pressure. So we can then state that the partial pressure of oxygen, as we have it here, is 21 kilopascals. So let's look again at the alveoli gas exchange. So air is inhaled, and within the alveoli space, we've got 21 kilopascals of oxygen. Blood arriving in the pulmonary artery is known to be around about 5 kilopascals partial pressure of oxygen. So remember, we're using this instead of the phrase concentration. So we see that there's a strong gradient from the 21 to the 5, and the process of oxygen diffusing into the blood and being taken up by hemoglobin is called loading. That blood will then travel to the tissues where the oxygen is released, and that process is called unloading. Those respiring tissues, when at rest, have a partial pressure of oxygen in this region here, about 5 to 7 kilopascals, but a very active muscle would be down round about 3 to 5 kilopascals. So a strong concentration gradient here, a strong pressure gradient there as well. Let's look at this event here, the loading and then perhaps the unloading, in a little bit more detail. Overall, each hemoglobin molecule joins onto 4 oxygen molecules to produce HbO8. We would describe this as a saturated hemoglobin, and we would describe this one here as unsaturated. So that's for an individual molecule, but we can talk about the sample of blood as well in the same way, being saturated or unsaturated. A hemoglobin molecule has an attraction for the oxygen molecules, and they are attracted towards the heme groups, and they would form initially HbO2. Now the interesting thing about this is that the molecule HbO2 has a higher affinity for the next oxygen molecule than the original one here. So number 2 has a higher affinity for oxygen than the number 1 hemoglobin. And of course this would then produce HbO4. Now in turn, HbO4 has a higher affinity for oxygen than HbO2, and so it attracts the oxygen molecule more readily, and they are attracted and remain together more strongly. And of course, to repeat the pattern, HbO6 has a greater affinity for oxygen than HbO4. And so as we progress down, we have increasing affinity as we go from the unsaturated hemoglobin towards the saturated hemoglobin in the loading process. Now, if we then graph this relationship rather than a linear one, we end up with this sigmoidal curve here, like so. On this axis, which is known as the oxygen dissociation curve, or for short, it's known as ODC, we have a progression from unsaturated towards the saturated hemoglobin. On this axis here, we have the partial pressure of oxygen, concentration if you like, and here we have the degree of saturation of hemoglobin with oxygen. And so we can note these numbers here for later, where we see that at 5 kilopascals and 10 kilopascals of oxygen, the relative saturation which occurs. You'll perhaps recall that in the lung, the actual partial pressure of oxygen is 21 kilopascals of oxygen, which is considerably greater than required in order to get full saturation. The implications and interpretation of the oxygen dissociation curve will now be explored in further videos. The links are shown below.